Hello ladies and gentlemen, my name is David Hills, the Scientific Director for Separation Science, and I'd like to welcome you all to our latest webinar. Our topic today is Ultrasensitive Silicate Analysis in Process and Boiler Water. Before we begin, I'd just like to cover some housekeeping issues. If you look below the play window, you'll see a black Ask a Question button, and you can ask questions at any point during the presentation by clicking the button, typing them into the pop-up window and clicking the OK button. Questions will be answered at the end of the formal presentation, and any questions that we don't cover may be answered offline afterwards by the speaker. Please note that submitted questions are not seen by the other attendees, so don't be shy about asking them. You'll also notice a full screen button in the lower portion of the play window, and you can press this if you'd like to view a larger version of the presentation. Please note that you may need to alter the aspect ratio of your screen to avoid the presentation appearing stretched in the full screen view. This presentation will be recorded. You'll all be sent a link to the recording when it's ready. And with that out of the way, let me introduce our presenters for today's webinar. I will first hand over to Carolyn Klein, who will give a short introduction. Carolyn has been working at Merck KGaA since 2010 and is the Global Product Manager for SpectraQuant spectrophotometers and photometric test kits for sensitive measurements, mainly in drinking and process water. Her focus is on the development and introduction of innovative products in the framework of photometric water analysis. Carolyn will then hand over to Bruce Herzig. Bruce is an application scientist at Millipore Sigma in Cincinnati, Ohio. Bruce has been with Millipore Sigma for the past 11 years, and previous to his application scientist role, he has held positions in QC and product development. Prior to Millipore Sigma, Bruce worked at Roman Haas as an analytical chemist and as a research chemist. And so, without further ado, I'll turn the presentation over to Carolyn Klein. Carolyn?
Thank you, David, for the introduction. Welcome from my side to today's webinar on ultrasensitive silicate analysis in process and boiler water. This webinar will be mainly held by my colleague Bruce Herzig in US. And I want to introduce a little bit more about Merck. We are Merck. The only exceptions are in United States and Canada. The life science business of Merck, Darmstadt, Germany, operates in United States and Canada as Millipore Sigma. Healthcare, life science, and performance materials are our core businesses. And in all three sectors, we offer specialized and high-quality products. We are one of the oldest chemical and pharmaceutical companies, and we have been around for almost 350 years. The silicate measurement, ultrasensitive silicate measurement, is very important because silicate becomes a deposit on internal surfaces of turbines. It is a topic for power plants and other process water cycles where we need ultra-pure water in a process. We cannot measure zero, but we can measure very low values with the method that my colleague Bruce Herzig will present today to you. So I will now hand over to Bruce Herzig. Bruce.
Thank you, Carolyn, for the nice introduction. So there's a picture of me. I've worked for the company for 11 years, got some experience in various things, R&D, analytical product development, and now I'm working as an application scientist. My focus is on point-of-use analytics, Carl Fisher analysis, and I'm based in North America. So, silicate analysis. We want to keep silicate as low as possible to avoid scaling. Why do we measure silicate? Well, it is important in industrial processes, particularly steam generation, where the component of scale buildup in pipes and boilers and turbines can cause problems. Buildup of scales leads to inefficiencies in these systems and increased operational costs. Silicate in water forms silicic acid, which then reacts with other elements such as magnesium, calcium, aluminum, and iron, and these form scales. These are slightly soluble. Scales contribute to formation of scale in industrial processes, as I mentioned before, and this is particularly a critical issue in high-pressure boilers and turbines. Too high of a silicate level in water would increase your blowdown frequency and increase maintenance costs as a result. Ultra-pure boiler water is required for high-pressure systems. Silicate testing is part of water quality analysis for these systems. In this slide, we have a schematic of a boiler system, and you can see the squares that are highlighted in blue with silicate in them. Those are potential test points for silicate, and as you can see, there's a number of other elements that can be tested as well, and Merck offers test kits for all these items. Silicate is potentially going to cause problems with buildups in any of these transfer lines between the various points in this process and on the turbine blades itself. So these are the reasons why we test for this. One high-end instrument used for the determination of silicate in water is a graphite furnace with atomic absorption spectroscopy. This is also called a GFAAS. This method is very sensitive and can allow a determination in the ppb range. We chose this method as a reference analysis to our photometry experiment. This method is based on the vaporization of atoms in a graphite furnace. The atoms absorb a characteristic wavelength of light from an emitted light source, which can be measured and is proportional to the concentration of the element in the sample. GFAA requires a high level of technical skills, where photometers are mostly simpler and easier to use. The photometers are typically in place in a lot of labs that are doing water analysis, and photometric applications have ranges covering 0.00025 to 1,070 milligrams per liter, which is equivalent to 0.25 micrograms per liter. On the graphite furnace, the limited detection on the instrument we have at Darmstadt at Merck is 1.93 micrograms per liter silicate. So you can see that we can get a much lower detection limit using photometry than with the graphite furnace. The new ultrasensitive photometric method using silicon-molybdenum blue is being described here in this webinar. This is an ultrasensitive method using a SpectraQuant-Proof 600 and a 100 millimeter cuvette. The measurement range with the 100 millimeter cuvette is 0.25 to 250 micrograms per liter of silicate. The method is pre-programmed on the SpectraQuant-Proof, and the 100 millimeter cell can only be used in the SpectraQuant-Proof 600 instrument. In the case of silicate in boiler and process water, we need to avoid the deposits of silicate, and to do that, we can't allow the silicate concentrations to exceed 20 micrograms per liter of silicate. Depending on operating conditions, some processors may want the silicate level to be even lower, such as 10 micrograms per liter or less. And with this new ultrasensitive method, we can achieve those levels. So the way this method works is in sulfuric acid, solution of silicate ions react with the molybdate ions to form a yellow heteropoly acid. This is reduced to silicon-molybdenum blue and forms an intensive blue complex, which can be measured photometrically. The method is analogous to APHA 4500, DIN 38405-21, ASTM D859-10. So the measurement procedure we used is described here in this slide. Different tests were performed in order to increase the accuracy in the lower range of measurement with this test. One thing it was found that improved accuracy would be pipetting the reagents SI1 and SI2 instead of using the dropper method. So for all future batches, the measurement procedure here is adapted to using pipetting to increase the accuracy of the lower the measurement range. So in this case, you take the pre-treated sample of 20 milliliters, and you must use a plastic vessel so that you do not get silicate contamination from glass. You pipette 200 microliters of SI1, add it and mix. The pH range at this step must be between 1.2 and 1.6 pH units. If necessary, you can adjust the pH with additional SI1 reagent. You allow the mixture to stand for 5 minutes. This is called reaction time A. After that time period, you will pipette 200 microliters of SI2 and mix, and then you will pipette 1 milliliter of SI3 and mix. At this point, you leave it to stand for 5 minutes. This is called reaction time B. And at the end of 5 minutes, then you transfer this solution to 2 separate 100 millimeter cells, one for the blank, one for the measurement sample, and measure immediately in the photometer. Again, this procedure must be performed in glass vessels. Of course, it is okay to use the quartz cuvettes or glass cuvettes for the measurement itself in the spectrophotometer. So we did a comparison of graphite furnace to atomic absorption spectrophotometry. The results that we obtained using the SpectraQuant silica test 101813, and we tested 5 different water samples. These results are compared below in the table. Ultra-pure water, you can see that for the graphite furnace, the detection limit of 1.93 the sample was lower than that. In the case of the ultra-pure water using the SpectraQuant test, it was also lower than the detection limit, which is 0.25 micrograms per liter. So this kind of trend continues in the DI water and the double distilled DI water, where the graphite furnace values are below the detection limit, yet in the SpectraQuant silicate test, you can see that we are actually able to detect levels of silicate here that are much lower than what we see with graphite furnace. You can also see that for the steam water and the boiler water, the results of the 2 tests are comparable, but not exactly correct. They do lie within the 95% confidence interval of the test kit, which is 3.33 micrograms per liter. So we did an experiment by standard additions to check recovery, and we spiked 5 different samples, which were the 5 we just discussed. And in here you can see that the deviations of the results from the expected result for recovery were quite close to the results we're looking for. And all deviations lie within the confidence limit of 3.33 micrograms per liter for the SpectraQuant test. So for calibration, standard additions were calculated using the pre-programmed method found and approved. And as I mentioned earlier, this has a concentration range of 0.25 to 250 micrograms per liter. So recoveries of the standard addition were acceptable, but they could be a little better. But what we found is it is possible to get even more accurate results with the Merck KGAA Darmstadt test kit. And we do this by creating a user calibration with a more narrow calibration band. So Here's an example of that calibration. We did 10-point calibration in a range of 0.5 to 25 micrograms per liter of silicate. We had excellent linearity of 0.9998, and what we found was that our confidence interval went from 3.33 with the pre-program method down to 0.45, which is going to give you much better confidence in your results and a much better detection limit, which standard deviation was also good, and coefficient of variation was acceptable on this test as well. More accurate results were achieved using the user-defined calibration than with the pre-program method. We go back and we look at the 5 samples that we had examined previously, and we can see now that we using the SpectraQuant test, now our ultra-pure water is again below the detection limit, and the DI water and the double distilled water are also below detection limit. And this detection limit is considerably less than the graphite furnace detection limit. You can also see on here that the steam water from a power plant and boiler water from a power plant, now the results are much closer together. And this is a result of having your own calibration in the area of concentration that your samples are at. So this gives you an opportunity to get a much more accurate reading on silicate. So standard edition shows that the deviations are much lower, and with the SpectraQuant silicate test 101813 and the user-defined method. So we went from this, we went and repeated our spiking experiment that we did before, and each sample was spiked with 3 different concentrations, which was what we did before. And now you can see that on average, the deviation is now 0.029 micrograms per liter, indicating a reduction from the original value of 0.94 deviation. So this result is coming in much closer to expected results, and this is all due to this user calibration that we've defined. So, in summary on here, photometry is a reliable and sensitive alternative to GFAAS. Test kit can be used instead of graphite furnace. It's less complicated sample prep than you would have for a graphite furnace. A pre-programmed 10-point calibration saves time and cost, but by using standard addition, it's demonstrated that the photometric kit produces reliable and accurate results. We also have capability for a 50 millimeter cell. We haven't mentioned that up to this point. The measuring range for that is 0.5 to 500 micrograms per liter. And with the 100 millimeter cell, which can only be used with the Proof 600, our measuring range is 0.25 to 250 micrograms per liter. And now we will go back to Caroline, and she will talk about our SpectraQuant Proof instruments.
Thank you, Bruce. Okay, I want to tell you a bit more about the Proof spectrophotometer family. We heard a lot about the silicate application, which is pre-programmed on the Proof spectrophotometers. There is the Proof 100 instrument, which is for routine applications. It's the best choice if you want to measure the SpectraQuant test kits or other test kits or methods in the VIS range. If you have intensive use during the day, or you also want to measure methods in the UV range, the Proof 300 is the ideal choice. And if you want to measure very, very sensitive, like in case of the silicate, you should choose the Proof 600 because it has also the possibility to measure in 100 millimeter cell, and it has excellent resolution and sensitivity for more sensitive measurements in, for instance, process water analysis. Yeah, what's special about the Proof spectrophotometers? One important thing is the Live ID barcode, which you can see right in the middle of the slide. It's not just a 2D barcode. We do not only store the method number here and the calibration data in the 2D barcode, it's much more. We print it directly in our production, and this means we have a lot of specific data inside the 2D barcode. It's really lot-specific data, and the big advantage for the daily analysis is that because of the lot-specific calibration data, it makes measurements most precise and avoids entering any corrections or doing updates to the calibration function. This saves a lot of time, and also you can be sure that everything is done for you, and latest calibration data are in the barcode. You just have to put the sample into the cell, wait, and then measure. You measure the cell by pressing it into the cell shaft of the instrument. These 3 steps are done, and then you have directly the result on the screen. The Live ID barcode is not only available for cell tests in the round cell, but also for reagent test kits. That means if you measure, for instance, the silicate in the 100 millimeter cell, you can also use the auto selector with the Live ID barcode and can select the method and the latest calibration data. This is really unique in the market. I mentioned already the long life lamp of the Proof 300 and 600, which is a xenon lamp, and it has a very long lifetime. And also in years of frequent usage every day, this saves maintenance costs because you do not need to exchange the lamps. We made it also with robust surfaces, and you can very easily clean the cell shaft just by removing it. This is very important, and it makes you in your daily life, it makes your life easier during your daily lab work. What can you do if you do not have a proof spectrophotometer? But Bruce talked about the silicate test kit today and very sensitive silicate measurement, and you just want to test it. You can go to our website, which is macmillipore.com or emdmillipore.com, and you can download our programming data for all our test kits. So the silicate test kit is also available on this list, and you just open the document, you see all the calibration data, you can program it on your own spectrophotometer, and you just go on and do your measurement. Thank you for joining the webinar today. If you want to know more, we have listed here several links where you can get more information about WFA applications. You can get more information about the proof instruments, the proof spectrophotometer family, and as well the full catalog with all the products. I want to say thank you also to my colleague Bruce Herzig from United States for the presentation today, and I want to hand over to David again.
Well, thanks, Carolyn, and thank you very much, Bruce, for those excellent presentations. We now have time for a few questions, and as a reminder, if you have any questions, now would be a very good time to send them in. And to do that, simply click on the black Ask a Question button below the play window, type in your comments, and click OK. So, Bruce, the first question we have is, in the presentation you talk about measuring silicate in boiler and process water. Can this test be used for other applications where I'm measuring silicate, for example, workplace monitoring for respirable crystalline silica?
Sure. This test is typically designed for aqueous solutions that contain silica. So it will work if the silica is in solution or could be put in solution. My understanding of industrial hygiene monitoring for silica dust is that it's typically captured on airborne dust filter, and the measurement is typically done by X-ray diffraction. So that would be an application that would have to be developed internally here at Merck or by the customer.
Thanks, Bruce. Our next question is, can this test kit be used with any UV-based spectrophotometer?
Yes, it can be used with any UV-Vis spectrophotometer, provided it can accommodate a 100 millimeter cuvette. In this case, the user will be able to use programming data that we can provide for our test kits to be used with other photometers. However, with other instruments, you will not receive the advantage of over 200 pre-programmed methods for silicate and for other parameters.
Okay. Another question we've received is, does Merck offer the standards required to prepare a calibration for low-level analysis?
Yes, we do. We offer certified reference standards in concentrations of 0.1, 0.5, and 1 milligram per liter of silicate. And from these standards, you could make standards in any range that you needed to dilute them to.
Okay, thank you, Bruce. And I think the final question we have is, for a user-defined calibration, how many calibration points should be done?
Okay, well, as you saw in our presentation, we did 10 points. But generally, if you have 5 points, that's an acceptable amount to get a good linear calibration. It's really up to the user and their internal processes, what kind of choices they make on the number of calibration points. But we wouldn't recommend anything less than 5 typically.
Okay, well, once again, Bruce, thanks very much for your presentation today. If anyone else has questions, we're going to leave the system open here. So if you want to submit your questions over the next few minutes, we'll leave everything ready for you to be able to do that. Thanks also to our scientific partners in this event, being Merck KGaA, or Millipore Sigma in the US, for all their technical input and support. And finally, I'd just like to remind everyone that a recording of this event will be available shortly, and you'll all be sent a link to it as soon as it's ready. And so with that, I'd like to thank you all for logging in and listening. Thank you and goodbye.